Good morning, everyone. And this class is about damping. We will see damping, the theory of damping, damping coefficient, and damping time constant. Here you can see the this one, the oscillatory motion when there no damping is present. You can see that the amplitude of the oscillation remains a constant in the absence of damping. Whereas when there is damping, as you can see in this diagram, the amplitude of oscillation will keep on decreasing, and this is due to the loss of energy of the oscillating body because of the presence of the damping medium or the damping force. So we will see the theory of damping. In general, you can talk about damping like this. If a damping force acts on an oscillating body, the oscillation will gradually die out. So damping force is a frictional force. It is dissipative in nature, which means the energy of the oscillating body will be lost due to the presence of the damping force. And that is the reason why the amplitude of the oscillating body keeps on decreasing. And actually, if we want to, if you can apply an external force, a periodic external force in order to restore the lost energy, then we can maintain oscillations without any reduction in amplitude. That we will see later, in that is specifically called forced oscillation, but right now we will see what is the effect of damping. So we will set up a theory. It is very easy to set up a theory for a damping. The assumptions involved are when the velocity of the moving body is small, then the dissipative force, an example is a frictional force. Okay, the dissipative force will be proportional to velocity, and since it tries to oppose the motion of the body or the movement of the body, we can say the direction of that dissipative force will be opposite to the direction of the velocity. So we use this equation. The damping force is proportional to velocity, and that proportionality constant, here we use the symbol gamma, that is referred to as the damping coefficient. Negative sign indicates that the damping force is acting opposite to the velocity of the body because it tries to stop the movement of the body, and that's why we use a negative symbol here. So in order to set up the equation, what we assume is that if there are no external forces present, then we can write the net force acting on the system, and it can be written in terms of the acceleration of the body, which is dv by dt. So you can say m into dv by dt is equal to negative gamma into v. So this is the force acting on the body, and this is the damping force which is present. This force is due to the movement of the body. That means if it has got a particular velocity, its acceleration is equal to dv by dt, and force is equal to m into a. And the only external force which is present is the damping force here. So what we do is we rearrange this equation. We can group together the velocity term on one side and the time term on the right side, so that you will be able to perform the integration like this. So we have got dv by v is equal to minus gamma by m into dt. So you can see that it is very now it is in a convenient form. Okay, so this equation, in order to solve this equation, we do integration on both sides. We have grouped together, or we have separated the variables velocity on the right hand side, so velocity on the left hand side. So the left hand side, these terms dv by dv should be integrated with respect to velocity, and on the right hand side the variable that we have is time, so this should be integrated with respect to time. So when you do that, here you will be getting log to the base e of v, and here you have got integration of dt is equal to t, and this gamma by m is a constant. So now then what we do is we will put gamma by m is equal to 1 by 2 because we want to express it in terms of tau, where tau is the time constant for damping. It is also referred to as the relaxation time. So then we will get the equation log to the base e ln v is equal to minus 1 by 2 into t. Now, considering the upper and lower limits of time and velocity, we can modify that result as ln v by v0 is equal to minus t by 2, which gives you the answer. V is equation for velocity in the presence of damping as v is equal to v0 e raised to minus t by 2. So this exponential function, it indicates that the velocity will be decreasing exponentially as represented in this graph. We have got time along x-axis, velocity along y-axis. Initial velocity is v0 at time t equal to 0. And if you examine this equation, you will see that when t equal to tau, v will become v0 divided by e. So that is what is shown here. When the velocity decreases to 1 by e times its initial value, the time taken will be equal to tau, and that can also be that can also be used to define the time constant for damping. Or you can say that time constant for damping is the time taken for the body which is experiencing a dissipative force. For that kind of a body, the time taken for its initial velocity to decrease to 1 by e times its initial value, then that time taken is referred to as the time constant for damping. Now, there are certain points that I would like to bring to your attention. The damping coefficient that I have used here is gamma. I have used that symbol because that is a symbol which is used in the study material I provided to you. But in different textbooks you will see different symbols. But what is important is that if we examine the previous equations, we know that damping force is equal to negative gamma into v, where v is the velocity. So if you set up the unit for a damping coefficient, it will be newtons divided by unit of velocity, so that will come out to be Newton second per meter. Okay, or you can define the damping coefficient as the dissipative force experienced per unit velocity, because when you put velocity equal to 1, you will get F is equal to gamma. So damping coefficient is the dissipative force or the resistive force experienced when the velocity is equal to 1. So that can be used as a definition for a damping coefficient. So correspondingly you will get its unit as Newton second per meter. So why I'm saying this is because if you want to refer various other study materials, you will see different symbols in different textbooks, and in different if you would like to explore videos or any online study material, you will see different symbols. Most common symbol that is used is actually C, but I don't want to use it here because I just want to follow the textbook which I gave you, because you have taken the copy. So in that textbook already the symbol C is used in another context. So that is it. So in the next class we will see how damping effect can be incorporated into a body which is executing simple harmonic motion, and we will see how we can prove that the amplitude will keep on decreasing but the oscillations will be maintained. Okay.